Hello and welcome to the video on related rates. Our objectives for this video are 1, to find a related rate, and 2, use related rates to solve real world life problems. One of the keys to doing related rate problems is going to be taking formulas that you are familiar with, that you've used in other classes, and like area formulas, Pythagorean theorem, just really any of these formulas. And we're going to use those things, and we're going to take the derivative of that formula with respect to time. So keep in mind that every variable in the problem is going to be a function of t. So we're going to be using implicit differentiation quite a bit in related rate problems. First thing I'd like to do is just kind of refresh our memory what about implicit differentiation, and we're going to go through and take the derivative of these three formulas here that are should be familiar to you. The first one is the Pythagorean theorem, the second one is the area of a circle, and the third one is the volume of a cone. And we're going to take the derivative of each of these with respect to time. So keep in mind that we want to use the chain rule when you take the derivative, and in this case, there's not going to be at any moment where a variable is going to match up with t. So each time you've got to treat, like in the first one, you've got to treat a, b, and c as functions of time. So what I'd like you to do is pause the video and take the derivative. Use implicit differentiation. Take the derivative of all variables with respect to time. In the first one, which I've already done here, and I hope that you've done yours as well, I had to go through on this one and use the power rule and the chain rule on this. So when I have a squared, that derivative, the derivative of something squared is going to be 2 times that something, times the derivative of a with respect to time, so times dA dt, plus 2b times dB dt equals 2c times dC dt. Now, one of the things I do on a problem like this is I'll go through and divide through by 2 just to eliminate those 2's. Anything common that's going to just get in the way, constants like that, just get them out of the problem. And so I get a times dA dt plus b times dB dt equals c times dC dt. In terms of the next problem, number 2, when I take the derivative of that, please keep in mind that pi is a constant. Treat it just like a 3 or a 7. It is a constant value. So when I take the derivative of both sides with respect to t, I'm going to get dA dt is equal to the derivative of r squared is going to be, it will be 2 pi r times dr dt. And now in the last problem, you have to keep in mind on this one that we do have a product here, r squared h. Both r and h are functions of t. And so when I take the derivative with respect to time on that one, I will get dv dt equals pi over 3 times, and in this case I have to use the product rule. It'll be the derivative of the first, which will be 2 times r times dr dt times h plus the first r squared times dh dt. Now, as you go through on these, each time you have to take a look at the information that you're given, what you're trying to find, the rates that you know, and in some cases you may have to go through and try to identify some sort of relationship that you can use to rewrite a problem, especially on a problem like this one where I had the volume as in terms of r and h. Try to rewrite that problem in terms of just r or just h based on some information, additional information that you're told in the problem. When you're asked to solve a related rate problem, there's a few steps that you want to go through as you work on these. The first one, you need to identify all given quantities and quantities that you know you're going to have to find. Okay, identify each one of those. I'd have variables in place for those that are variables. Anything that's constant, make sure you identify it as being constant. And then you make a sketch. Make a sketch of the problem. And then make sure you label that sketch with the information that you have. Also, please note any rates that you happen to have in the problem, and determine where those are and how those fit into the diagram that you have. Number 2, you want to write an equation involving the variables whose rates of change are given, or the one that you need to determine. Okay, now here is the key part. Please notice up here that you're not plugging things in for the variables. Okay, if you've recognized something as being constant, you want to make sure that that is in the problem early on. But variable values are not plugged in yet. That third thing, and that's why I have it in red, is real important. You're going to want to use the chain rule to implicitly differentiate both sides with respect to time t. You're going to take the derivative of your equation that you wrote in the second step here with respect to time. Now, once you get finished with that, after you have that derivative, we move to step 4. You're going to substitute every known value in for the variables and rates of changes. Anything that you know. Some of the rates you'll know, and you'll know enough information about the variables to be able to fill those in as well. And then once you've substituted all that in, you need to go and then solve for that required rate, the one that they're asking you to find. Let's take a look at a problem. We have a spherical balloon that's being inflated with gas at a rate of 800 cubic centimeters per minute. And we want to know how fast is the radius of the balloon increasing the instant the radius is at 60 centimeters. Now, the first thing I want to do is I want to identify the information that I'm being told in this problem. Now, the one thing I notice right away is I do have a rate, and the rate that I'm given is right here of 800 cubic centimeters per minute. And that is really a rate of change for the volume. So right now, I know that dV dt, the rate of change of the volume, is equal to 800 centimeters cubed per minute. Okay, and I know this is a spherical balloon, and so the information I know on this one is that the volume of a balloon, and I know I want to use volume because I'm giving it a rate of change for the volume. The volume of a sphere is the equation V equals 4/3 pi r cubed. And so what they want to know is they want to know how fast, I'm being asked in this case to find how fast the radius of the balloon is increasing. So I want to find in this problem, I want to find dr dt. And I want to do that when r equals 60 centimeters. So what I'm going to do on this is I know that my formula, that I have a volume formula, is 4/3 pi r cubed. I'm going to go take the derivative of that with respect to time. Actually, I want you to go and take the derivative of that with respect to time. So pause the video and do that. And once you have that derivative, come back and we'll complete this problem. Welcome back, and you can see right now that I have already gone through and done the derivative just as you have. The volume again is 4/3 pi r cubed. Now when I take that derivative, dV dt is going to be 4/3 pi times the derivative of r cubed with respect to time, which is going to be the 3r squared times dr dt. And when I go and simplify that, the 3's will go and cancel each other out. And so dV dt is going to be 4 pi r squared times dr dt. Now what we need to do is go through. I didn't draw a diagram on this one, mainly because I know it's going to be a circular, I just have a circle on there. Couldn't really draw a balloon necessarily, but what I'm going to do at this point is I'm now going to plug in the information that I know and then solve this for dr dt. So what I know right now, I know this equation right here. I've taken my derivative. I know that dv dt, so take that, I'm going to break this up, dv dt is 4 pi r squared times dr dt. And in this case, I happen to know that dv dt is 800, and I know r is going to be 60. So I'm going to plug that information in. So I'm going to get 800 equals 4 pi times 60 squared times dr dt. So when I go through and multiply the 60 squared times 4, I get that 800 equals 14,400 pi times dr dt. So what I'm going to have to do now is divide by the 14,400 pi, both sides. So when I do that, I get that dr dt is equal to 800 over the 14,400 pi. And when I put that into my calculator, I come up with this to be about equal to 0.0177. And in this case, that's going to be centimeters per minute. And I know it's going to be per minute because our original rate in terms of volume was given in cubic centimeters per minute. So our time unit in this case is going to be minutes. So I'm going to be increasing, in this case, I know I'm increasing the radius by 0.0177 centimeters per minute. Now let's look at another problem. A balloon is rising vertically above a level straight road at a constant rate of 1 foot per second. Just when the balloon is 65 feet above the ground, a bicycle passes under it, going 17 feet per second. How fast is the distance between the bicycle and the balloon increasing 3 seconds later? Okay, so in this case, again, we need to identify the information that I know. And I know that the vertical change for the balloon, I know I have one right here of 1 foot per second. I also know that the bicycle is traveling at 17 feet per second. And I know that, and this is another part that is key on this one, I do know that the balloon was 65 feet above the ground when the bicycle passed directly underneath it. And what we're looking at is what's happening 3 seconds later. Well, with the 3 seconds, I am able to determine how high the balloon is because I know that the balloon the balloon was at exactly 65 feet when the bicycle went under it. So I have, since the balloon is increasing, raising at 3 feet per second, after 3 seconds, it's going to be another 3 feet higher. And I know that the bicycle is traveling at a constant rate of 17 feet per second. And so I can go through and determine the length, how far that bike has gone, where that bike is at 3 seconds later. So now what I'm going to do is I'm going to pause the video. I'd like you to pause the video too, and I'd like you to go and draw your diagram that you feel would be good to, could be used to illustrate this problem, and make sure to label all the variables. Please don't put in the exact values that we know in terms of what happens 3 seconds later, but put that information, put label the variables as, and give me a diagram for this problem. Okay, now I have my diagram, and I hope you have yours as well too. What I have in this case is I have a balloon that I know is going up, and you'll notice here that I've labeled my rate showing that it's going up at 1 foot per second, and that's going to deal with the height h of the balloon. I know my bicycle in this case is going to be b feet from the spot directly underneath the balloon, and I know that its rate is 17 feet per second. So in this case, what I know is that I have that dh dt is going to be 1, and I know that db dt is going to be a positive 17. And both of those are positive because H and B are growing. If they were getting smaller, then we would need to use a negative rate. Okay, and what I'm looking at here is, for this problem, is I need to identify what D is. I actually want to know what the derivative, or what D prime actually is going to be. I'm going to use probably D prime on this one, otherwise, because I did label it D as a distance, and it would be dd dt. I don't know if it really looks and conveys the information exactly how I want it that way. So I'll probably use the prime notation on this problem. So what I know in this case from the diagram is that I know that I see a right triangle there. And so I know that h squared plus b squared is equal to d squared. And then taking the derivative now of that with respect to time, I know I will have 2h times dh dt plus 2b times db dt, which equals 2d times, and I'm just going to use, like I said, d prime on this notation. I could have used h prime and b prime there as well, but I'll use definitely d prime for that other one. And now what I can do is I can go through and drop off the 2's. That works. So I'd have h times dh dt plus b times db dt equals d times d prime. And what I'm really going to be looking to find is d prime. Now what I have to do is take the information that I know. So once I have that derivative, remember on here, the first, number one, give a diagram, label the information. Number two, come up with this equation that you can use, that you're going to have to take use implicit differentiation with respect to time, and actually go through and take that derivative with respect to time. The last thing I need to do is I need to go and plug the information that I know into the problem. So here's what I know. I know that dh dt is equal to 1. I know db dt is equal to 17. I know the instant that we're talking about here that h has got to be at 68 feet. And I know b has got to be at 51 feet. And so, because it's changing at 17 feet per second, multiply that by 3, you get 51. The only other thing I have to do is I have to find out what d is. Well, I do have the Pythagorean theorem, and so I'm going to use that to find out what d is. So, using the Pythagorean theorem, I noticed in this case too, with the information I had, that since b would be 51, which is 3 times 17, and h is 68, which happens to be 4 times 17, I know that the d, that distance d, has got to be, by the 3, 4, 5 family, has got to be 5 times 17, or come out to be 85 feet. So plugging that information in to this problem, I now get h is 68, 68 times 1, plus 51 times 17, equals 85 times d prime. And so what you want to do now is solve for d prime. When I do the calculations of 68 times 1 plus 51 times 17, I find that this whole piece right here comes out to be 935 equals 85 d prime. Divide by 85. And I find that d prime in this case comes out to be 11. So in this case, I know that the distance between the balloon and the bike is changing at a rate, is increasing at a rate of 11 feet per second. That is the rate that the distance between the balloon and the bicycle is changing. This now gives you a couple of examples of a related rate problem. We will do a couple more examples in class along with some problems from the book. So please make sure that you have an understanding of each one of these problems. You may want to spend a little bit of time looking at some of the examples in the book, but otherwise we will go through a couple more examples, like I said, in class on the next time, and then we'll spend some time working on just various related rate problems in the book. Some that might be have a little bit more of a a little bit more interesting characteristics to take into account as well. So, hope you have a good evening, good morning, or wherever the day is, what part of the day it is that you're in right now. And we will see you in the next class.